Everybody got a copy of this? You guys go on question 1, please. I'll give you a few minutes and see if you can do question 1. Right? Yeah, that's fine. You need to follow the question. I don't think the question is that. The question is here, in question 3. You need to follow the hint here. Try to use this hint. It will be not simpler if you use this hint. Why this is wrong? Because this is not equal to this. No, it doesn't matter. This doesn't matter equal to this. Because remember, the variance of x cannot the variance of x is equal to rotation of x times the fx squared. This is the definition. And what you have here is not the same as this. They are not the same. No, they're not. X bar is the cyclic mean, and this is the potential mean. They're not equal. Yeah, because the bias is equal to 0, MSC is the same as remember what we did last week. It's a bias, the estimators are unbiased. In other words, the bias is equal to 0, then the variance is the same as MSC. So what we computed here, this is equal to the MSC of V1 half. And this is equal to the MSC of V2 half. Are you done with question 1, guys?
Yeah, those biscuits you were talking about. Do you get a biscuit budget from?
No.
Oh, you've got to spend your own money.
I know, 7 days, isn't it? 7 days.
That must be like 80p a week. Devastating.
Half a week, you know. That's what we buy. We mix it up. This week it was these, and then Amber and Beth bought chocolate digestives as well.
Shit.
Obviously they got the better one. I just try and buy, like cheap generic biscuits. You want to feed everyone. You don't want to buy like one biscuit each.
No.
You want to have the quantity and the variety.
These are probably two of my favourite biscuits. Great choice.
Good choice. We've got to have vegan ones as well, so we've got to have both ones.
How come? Do you have a vegan?
It's kind of difficult. You wouldn't think both ones would be vegan or vegetarian. Maybe it's vegan. Yeah, I'm pretty sure they're vegan.
Alright guys, let me show you how to do. I think many of you have already done.
Yeah, not bad.
Let you guys do question 1, please. Alright, let me show you how to do question 1. Right? Need my glasses just a minute. So you have you have three. If you haven't done question 1, can you listen, please? You have 3 observations from normal distribution, independent and identical, right? And you have 2 estimators for mu. The first one is this is the first estimator. The second estimator is this. The question is, which of these 2 estimators is better and why? I remember telling you last week on Wednesday how to do that. The first thing you need to do is to compare the biases. So I'm going to compute the bias of mu1 hat and the bias of mu2 hat. Alright, let's do this first. Remember, the bias is defined as this is the definition of bias I gave you last week. This is the expected value of yes, and this is 1/4 okay. Now we know that the expectation of x1, the expectation of x2 and expectation of x3, each of them is equal to mu, right? So this is quarter times mu plus 2 mu plus mu, right, minus mu. So this is clearly 0. Alright, therefore mu1 hat is an unbiased estimator for mu. And similarly, this is the bias of mu2 hat, and this is a third times the expectation of x1 plus the expectation of x2 plus the expectation of x3, right? And this is a third times mu plus mu plus mu minus mu, which is 0. So both estimators, mu1 hat and mu2 hat, have bias equal to 0, right? So there's nothing to distinguish between the 2 estimators with respect to bias. By the way, can you guys over there see this screen or no? Can you see it? No? All right, I'll switch. I will switch in a minute. Hopefully you can see this now, right? Yeah. All right. Now next page. Did you guys finish writing or not? You didn't finish writing? Oh, come on, guys. I'll put this online. And do you want this back on or what? Did you finish writing this or not? You did? Oh, come on, guys. Anyway, you can see this online in this evening. Come on, guys. All right. Just don't moan about it. I mean, all right. The next thing you need to compute is the MSC. Right. There's nothing to distinguish between with respect to bias. So the next thing you need to compare are the MSC, or the mean squared error. Now, because the bias is 0, the MSC is the same as the variance. Remember, I proved this last week. Yeah, MSC is equal to the variance if the bias is 0, right? So this is the variance of x1 plus 2x2 plus x3 divided by 4, right? And this is, now when you take a 4 outside, it becomes 16 times the variance of x1 plus 4 times the variance of x2 plus variance of x3. Alright, so this is the 16th sigma squared plus 4 sigma squared plus sigma squared, which is 4 sigma squared. Sorry, am I right? Sorry, 3 sigma squared divided by 8. Is that right, guys? Did you follow what I've done here, right? Now, similarly, the MSC of mu 2 hat is the variance of mu 2 hat, which is the variance of x1 plus x2 plus x3 divided by 3. Take the 3 outside, it becomes a 9. So it's so this is 1 over 9 times sigma squared plus sigma squared plus sigma squared. So that is sigma squared divided by 3. Alright, guys, now let me ask you that you have the MSC of m1 hat equal to 3 sigma squared divided by 8, and the MSC
Mean
of
squared.
m2 hat equal to sigma squared by 3. Now, which one is smaller and why?
Error.
Huh? Come on, guys. You have this number, you have this number. Which of these two is smaller?
Sigma squared over 3.
Yeah, of course. Yeah. Right? Is that clear, guys? So of the two estimators, mu1 hat and mu2 hat, the better estimator is the mu2 hat because it has the smaller MSC, right? The biases are equal. The biases for both estimators are equal to 0. So there's nothing to distinguish between the two estimators with respect to bias. But with respect to MSC, This one is smaller than this one, and therefore needs to have the better estimate. Right? Okay, guys? Alright, can you do question 2, please, now? There are no questions. Can you do question 2, guys? Unless you have some questions for me. Has everybody signed the attendance sheet, guys? Yes? Oh, sorry.
What? Thank you.
Thank you. Yes.
I think that's a lot of people.
It's 30s or seconds. Good job answering the question. Step up to the line.
Yeah, so fucking good.
Smaller, isn't it? So smaller.
I heard like a gasp around the room because it was such a complex question.
And to step up.
Yeah, I don't think people expected that from me.
You need to use the thing to show that the variance of this is minimum when AI is that means the smallest possible value.
You should see how organised my notes are. It's insane. Kind of hope this isn't the microphone. Or the podcast. Oh, there's not a podcast, so this isn't. Good job. I'm thinking about doing pass next year. Do I need to apply?
What?
You know, for pass next year.
It's like Easter.
Oh, is it? Can third years do it?
Yeah.
You do it.
Someone wants to do it with me, I'll do it. Yeah. It's quite, well, it can be different, depends what your group's like. Very dependent. Like, this year we've got a pretty good, like, it's a mixture. You have to get a good group and you have to be good at so it's a lot of luck based.
I feel like by third year I should be okay at first year stuff.
You forget it all. You'd be surprised how much you forget.
Really?
Yeah. Like, the rank theorem, show me rank theorems.
The rank theorem. Yes, of course, the rank theorem.
You remember going over it, don't you? You remember knowing it, what it was. You don't remember it.
Is it from... Let's see if I can get what topic it was from. Rank. What's the rank? The rank theorem. Absolutely rank.
Linear algebra.
Linear algebra.
Yeah.
So what is it, mate?
Can't remember. Good. It just came up with a question today. But like, I'll tell anyone else, because you did a thing called like guided learning. So it's like, is anyone else in this question? And someone goes, yes. You go, could you explain it to us?
Oh, nice.
You can take the expectation inside.
So, helping them help them.
Some of AI times the expectation inside.
It's probably quite good for
Yeah.
just for the CV, right?
Yeah,
It's something very easy to put on it.
Yeah.
That makes sense.
yeah, that might. It's good fun.
To
be honest. In the day.
Are you still making Kahoots every week, or did that die?
But we're just being assessed next week.
Oh,
We played Countdown this week, too.
what's that?
The Countdown. The game where you do the numbers game and the words game.
You just played Countdown.
Yeah. It's a good pass section. We had prizes this week, little bags of Maltesers.
No, nice.
And then we played Geo yesterday at the end. At last 10 minutes. Came second by 50 points.
You can check it,
Yeah,
fine.
we did
Who came first?
Amber by 50 points. I was literally bought on until the last one, and it was this white bridge. Have you ever seen, it's a massive bridge. Basically, it's like,
Was it tall?
it's in front.
Just up the Milan suspension bridge.
Yeah, I don't know what it is. 30. I got that one. Got the rest.
Alright guys, could you listen to me guys? If you haven't done question 2, could you listen to me guys? Right, so you have xi IID with normal distribution with these parameters, and you have this estimator, that is sum of ai xi from 1 to n as an estimator for mu. The first part of the question is to show that this estimator is unbiased. To show that something is unbiased, you need to show that the bias of the estimator is equal to 0. Alright, so that's what I want to show. So I want to find the bias of the estimator, which is the expectation minus mu. So this is minus mu. Now we know that each of these guys here is equal to mu, right? Alright, so this is mu times, because mu is a constant, you can pull it outside, so it becomes like this. Now this is mu. Factor out mu. In brackets you have sum of ai minus 1. Alright? And this is equal to 0 if and only if the sum of ai is equal to 1. Alright, so that's what you are asked to prove in part 1 of the question, right? That the estimator is unbiased. The estimator is unbiased if and only if the sum of ai is equal to 1. I think most of you got that right. Most of you have done that question. Now the second part, let me put this over here. The second part is a little bit tricky. The second part is to find the variance. So this is part 2. Part 2 is to find the variance of the estimator. Okay. Now the simplest way to find the variance is to take it inside. So this becomes, if you take the variance inside, ai being constants will become ai squared times the variance of xi. You follow? remember when you take the variance inside, you need to square all the constants. So AI becomes the square of AI, right? Now this now we know that this guy here is equal to sigma squared. Yeah. Sigma squared is a constant, so you can pull it outside the summation sign. So this becomes sigma squared times this. Now I'm going to apply a trick here now, guys. I'm going to read the question, guys. It says, you should read the question. Let me put it just briefly here. You should read the question. It says that you can write the sum of AI squared as follows. I know you have the question in front of you, so you don't need to read this guy here. You can write yeah. Right, it's because by the hint, right, because of the hint that is given to you, you can write the sum of AI squared like this, okay? Yes. Now, the question is, we want to minimize this. We want to minimize the variance with respect to AI. Now, there's no AI here. The only term that involves AI is this term here, right? And this term here is a sum of squares of numbers. So what's the minimum possible value it can take? You have, guys, this is a simple question. You have here a sum of squares of numbers. If you square something, it can only be positive or zero, right? So what's the lowest possible value it can be? Zero, right? Yeah. So the minimum possible value of this term, right? The minimum possible value of this term is 0, right? And it will be equal to 0 if and only if AI minus 1 over n squared equal to 0 for every I, right? You see, this guy here will be exactly equal to 0 if and only if this guy here is equal to 0 for every I. And this will happen if and only if AI minus 1 over n equal to 0 for all I. Yeah? And this will happen if and only if AI is equal to 1 over n for all I. Alright? Hence, is it clear, guys, or no? Do you understand my reasoning, guys? Let me switch this. Let me switch this around. Do you guys understand what I have written? Or no?
Yeah.
So the reasoning is as follows. I mean, this term can only take values which are either positive or 0. So the minimum possible value is 0. It will be equal to 0 if and only if this term is equal to 0 for every I, right? And this reduces to the AI equal to 1 for every I. So the variance will be minimized if AI is equal to 1 over n for every I. So that's the question, guys. Can you do question 3 now, please? Hey, are you okay with it? You guys do question 3 now. Yes. We only try to minimize this because there's no real idea. Are you guys okay with that, or any questions you have? Are you okay with that now? No, you understand? Okay. Good. You guys okay with that? Yeah? Sure. You guys, good question? Yeah.
Dun, dun, doo, 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 doo.
That's for what I did, guys. Can you do question 3, please, now? For question 3, it will be easier if you can use the hint. There's a hint for question 3.
Ooh.
So, first bit doesn't help.
Everybody sign this.
Can you take the expectation thing inside the sum?
Yeah.
Should we give it a go?
It's a minus anyway.
Thank you.
That's what I've done, but it's
I'm on smile and nodding terms with Dennis Hopper.
I'm happy for you. How's this come about?
Don't know, actually.
Have you been talking to him on it?
No. We had like one talk about how the exam went. Now whenever I see him, I'm like, fine. He's like, hello. hello there.
Hello. Hello.
Yeah, just like that.
Yeah, just like that. How was your chat with him?
Yeah, it's always pretty good. Well, it was just like, he was just like, how did the exam go? And I was like, it was okay. It's quite hard. And he was like, yeah, I like to challenge my students. Cool.
When the results come out?
It's got to be this week, I reckon.
This week?
I'm surprised. How does nobody know?
No idea.
It's insane.
This was the best kept secret.
Yeah.
Our class group said let's get released on the 20th.
Yeah, I reckon it'll be. Oh, the 20th. I thought it was going to be like the 17th.
That's next Monday.
Lads.
You guys done question 3? Try to use the hint for question 3, guys. It'll be a lot easier if you try to use the hint.
No.
All right. Right, can you listen please? If you haven't done question 3, could you please listen? So you have xi, iid from a normal distribution with these parameters, and you have s squared given by this is sample variance as a possible estimator of sigma squared. The first part is to find the expectation of s squared. Right? Now the expectation of this all right, I'm gonna use a hint. You see the hint? Can you read the hint? Let me put this over here, guys. This is the hint. If you can see the question, guys, it says you see what I have done. Can you see what I have done, guys? I have multiplied by n minus 1, divided by n minus 1. I have divided by sigma squared and multiplied by sigma squared. Now I'm going to bracket this. I'm going to take it outside. All right. You see what I've done? Yes? No? I've taken this guy here outside the expectation because it's a constant. Now, according to the hint, this must have the chi-square distribution with n minus 1 degree of freedom. This must have the hint says that this must have the chi-square distribution with n minus 1 degree of freedom. Right? So, now, one of the properties of a chi-square distribution, we will learn that later on in the course. If you look at the lecture notes, guys, if you look at the lecture notes on trying to find out where it is. Not this one now. If you look at the lecture notes on page on page 16, if you look at page 16 of the lecture notes, the chi-squared variable, the expectation of a chi-squared variable with n minus with n minus 1 degree of freedom is equal to n minus 1, right? So these two guys cancel. So the expectation is equal to sigma squared. All right. Hence, this implies that S squared is unbiased for sigma squared, right? Because remember, since the expectation of S squared is sigma squared, the bias is equal to 0. and therefore S squared is unbiased for sigma squared. Yeah. Now that's only the first part. The second part, can I take this away, guys? Okay, put it here for those of you guys over there. The second part is to find the variance. The second part is to find the variance of S squared. So I'm going to follow the same approach. The variance of S squared can be written as the variance of like this. So once again I have multiplied by n minus 1, divided by n minus 1, divided by sigma squared, and multiplied by sigma squared. I'm going to put this in brackets. I'm going to take it outside, so it becomes squared times the variance of this Now, if you look at page 17, if you look at page 17 of the notes, if you look at page 17 of the lecture notes, you will see that the variance of a chi-squared variable with n minus 1 degree of freedom is 2 times n minus 1. Right? So this becomes 2 sigma 4 to the power sigma power 4 divided by n minus 1. Right? And this, as n goes to infinity, this approaches 0. So S squared is unbiased and consistent. Do you guys see this or not? Are you with me or not? Lost? No. Huh? Are you guys with me? Yes? Are you alright, sir? Yeah. Alright, let me put this over here, guys. Put it over there. Yeah? Down? Okay. Sorry. Alright, is this clear to all of you or not? If you have any questions, just ask me while I go around. Ask me any questions you have on this side. You guys okay with this? What about this? Are you okay with this? Okay. Can you do the next one? Question 4, which is the last one. You only need to do first part 1 and 2. Part 3 is not examinable. One.
These example classes are actually quite useful. These example classes are actually quite useful.
Okay. This is a hint. Yeah, you can prove a hint if you like. I will not prove it, but it's not difficult to prove. Yeah. Are you guys okay with this?
Is it not just the exponential distribution? Would that be minus lambda e to the lambda x, or is it lambda e to the minus x? Lambda e to the minus lambda x. Gamma.
What's the point of this bit?
2 gamma on the bottom. What's the point of 2 gamma?
No, I mean this equation.
That's the PDF.
No, I mean like What does it give you? You don't need to use it first, do you?
You need to find. You need to find mu.
Yeah, that's what I mean. Other than that,
So, yeah. And the only way you can find mu is by integrating that, right? Over the range. So we get the goal. That's how we get the goal. So productive coming to tutorials.
you're going to get minus.
A minus expectation.
No, it's just because you integrate, you just divide in by this, aren't you? So if this cancels, but you get a minus.
Yeah. True.
You set when you find the expectation, do you set it equal to 1 or? No, you use it.
Whenever you get 0, minus, because to the minus infinity, it'll be 0. And you get minus a positive value. Minus a negative value, which will be a positive.
This is the positive. So you get this first one. You get infinity minus infinity, which is 0.
Yeah, it's a formula. It's a formula from the module.
Should we give it a go?
This on page 17, page 17, variance of
Lucky.
Fine.
Yeah, so the new here is n minus 1. The new in this case is n minus 1.
Selection.
This formula can be put.
Very
I'll
tight
put it
there.
later on.
Oh, honey.
I'll put this formula later on.
Got karate as well. But it's not good karate.
It means distributed as. It means this simple here means this has square distribution with n minus 1 here. This simple here, the term that is simple means distributed as. Can I write here? This means distributed.
Oh no, the x disappears.
Distributed as.
Because you get x squared.
That's what it means.
Oh no, but you've got to differentiate that, yeah.
Yeah.
Then write it down.
Then you guys do question 4, please. Another question 4 is then you guys okay?
Does it differentiate to minus x over down?
I'll give you a hint about just a minute. Just before you go, I only have 1 minute left.
It's going up.
Question 4,
Going
you
up to
have
distribution. Was it just a letter?
It's just
part 1. You have the estimator gamma hat equal to 1 over 2n times the sum of xi squared, right? And you need to show that this estimator is unbiased. Right? To show that something is unbiased, you need to find the bias of gamma hat, which is the expectation of gamma hat minus gamma, and this is the expectation of, just give me a sec guys, I won't take long. Yet this is this, and this is 1 over 2n times the sum of the expectation of xi squared minus gamma. Now to find the expectation of xi squared, what you need to do is just integration, guys. So to find this guy here, you just integrate from 0 to infinity of x squared times the PDF, which is alright. I'm not going to do this integration now because I run out of time, of course. So, but what you need to do is to do this integration, right? and simplify the answer, you will get that this whole thing will reduce to 0, right? Eventually, right? After doing the integration, after doing all the integrations, you will see that this whole thing will reduce to 0, right? All right, guys. I'll see you guys in a minute.
Maybe you will.
What's he going to say?
Dunno.
Where was he at in the last section?
We just finished all this point estimation.
After likelihood.
I don't think we got to. Oh, did we get to? We've done MSC. Yeah, it might just be likelihood. Yeah, we didn't get to actually.
Big one back away.
Oh, I'm tired.
I think for now I'm going to finish these.
Why is that?
Because these are useful for lectures. We've done all the work already.
Do you want to share the final board?
Go for it. I've had literally that I've won the class before. No, literally. I've also got bags in my team.
Anybody
I'll
else
bid
like
you,
to
Jim.
sign the affirmation, guys?
Just persuading us to come together. I'm not coming to that. Yeah. Oh. It's good fun.
I had to get something
Pretty
in.
metro.
Yeah. It was yesterday's actually.
Just because it was yesterday doesn't mean it's
I've already done it on,
Rosen.
did it on another paper.
helicopter thing.
Yeah.
Spotted that from the distance. Crossword
Sniped it.
silver.
Good salami.